I forgot to check the YouTube viewership. Everybody take a look at the pre-recorded lecture. I'm sure you guys had nothing better to do. So you want a little bit of a quick review just to make sure everybody is on the same page. All right. Okay, so we are into differential equations. I'm going to go quickly through this part, and then I'm going to get to, honestly, what I consider to be one of the cooler parts of this. I'm a big nerd, apparently, because the cooler parts is like this mathematical phenomenon that a lot of you guys would be super bored by, but you're in my class, so okay, differential equations. Roughly speaking, we're going to classify them. We're going to split up initial value problems from boundary value problems. Of course, computers don't care if it's time or space. All they care about is the number of boundary conditions you have, right? So boundary value problems typically will have boundaries on either side of your domain. Initial value problems, you only have your time boundary at 0, right? Which means that you have to start somewhere and then you have to progress, and you can only step in one direction. Initial value problems are very common because it's time, right? There's a classification here for the different types of differential equations. I would say the important parts to know here are, okay, first of all, the ordinary differentials are obvious. Second order is obvious, right? It's all to do with the number of times that your dependent variable appears. So here you've got I'm sorry, I skipped over to the nonlinear versus linear. Okay, so this is second order because you've got the second differential. Over here, this is considered a linear one because you've only got y appearing by itself, or maybe some of its derivatives. So even though you've got di y squared by di x squared, it's still considered linear because you don't have anything attached to that. As opposed to di y by di x bracket squared, right? You're multiplying those two things. Now it's a nonlinear because now you have some dependence on your y function that's multiplied by something else. Linear is always easier. Nonlinear gets complicated, as you guys probably know by now, or at least you should. Okay, homogeneous versus non-homogeneous, not actually so relevant for our course because we just throw the numerics at it, right? IVPs are the important one. That's what we're going to be talking about this week. Next week, we're going to jump over to boundary value problems. And then we've got the ordinary ones, and we've got the partial differential equations where we're mixing the independent variables. Space and time, that one we're going to touch on, I think, at the end of next week. We'll get to that one. This is actually probably the most fundamental 3 points of this page and of large parts of this textbook. That being said, it kind of drifted right by me for a few years before I finally kind of sunk into what it is. Elliptic PDEs are ones that don't have time dependence, right? It's a much more general concept than that. It's to do with something called the characteristics of the differential equation. It's all about solvability. But for us, like meager engineers, elliptic PDEs don't have time derivatives. So you would say something like acoustics, right? Parabolic PDEs are our favorite, typically, right? Because you have a single time dependence, and then you can have second degree in space. So this is all of diffusion, heat diffusion, transport, all that fun stuff. Navier-Stokes falls into this, et cetera, et cetera. Hyperbolic are the hard parts. Those are the wave equations. So for the quantum types, right, like this is, you're all over this one. Ideally, you'd be able to break it down to the elliptic PDEs, but oftentimes you're kind of stuck with the wave one. As it turns out, most of heat and mass transport are actually waves anyway, so it actually should be this, but that's a whole nother level. Okay. So I'm going to zoom through this one, okay? Initial value problems are something that you have something like this. We're actually going to come back to this example, right? Di y by di t is equal to y. Doesn't get much more simple than that, right? Everybody knows the solution to this one, especially if that were a negative in there, right? This is exponential decay, exponential growth. Super, super easy. The initial value problem comes in because you have y at t is equal to 0 is equal to something. The important thing to note about these is that, and really the crux of the two methods that we're going to talk about, is that when you are going through time, effectively what you're going to be doing is you're going to be integrating from where you are now to where you want to be the next time. And with integration, the errors accumulate. Okay? So there's the big question mark of how when we're time stepping, we're accumulating the errors. But it gets much, much worse than that because there's a problem. All of our answers are wrong in numerics, right? They're all wrong. We just want them to be wrong as little as possible. But there's a new level that's going to be if does our wrongness, does our error grow or shrink? Okay, that's going to be, I'm going to get to that one in about 10 minutes when I actually start today's lecture. Okay, that's what we're going to talk about, right? It's all going to be about numerical noise destabilizing these solution schemes and what we can do about it. There are a few different ways. There are the ways that, so there are the single step methods. I think I put that, yeah, down here. Okay, single step methods say that you have the time right now and you want the time the next time. That's a single step method. A lot of these ones end up taking sub-steps. They'll just kind of like step along here, 1, 2, 3, 4, 5, and now you've achieved that one. And the name of the game is going to be how you leverage doing those additional calculations to estimate the higher derivatives. We're doing Taylor again, cancel out your errors and achieve approximate good order approximation. I'll sketch out that one. The alternative to this is something called multi-step methods. Okay, so single step methods say you are now, I want the next. Multi-step methods say I am now, but I also have a history. I know what my last 5 time steps were. Can I use that information to get a better estimate of what's next? Okay. Explicit methods are probably what you're thinking about when I say single step methods, right? What it says is that you have, let's see. Okay, so here's the math. Go through the math. No, actually, I should review that one quickly. Okay. The Runge-Kutta methods are the Newton Cotes of initial value single step methods. Okay, it forms the general like kind of framework for the analysis of this sort of thing. And the way it works is that you want to say that your next time step is your first time step plus some Taylor expansion in time. You've got your initial, you've got your step size, that's your delta t, your delta x, whatever, and you're doing some kind of Taylor, and you want to use that to find what your next time step is. And the way it works is that we're going to take that entire step, right? All these derivatives, by the way, y prime, because it's now a derivative in time, what we're going to do is look up to our equation or information that we have, and we're going to say, well, actually, we have dy y by dy t. That's given by the differential equation. We're using the differential equation itself, f of t and y, and we're going to plug that in. Okay, so we're going to say yi plus whatever equation we have times the step size, boom, 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 boom. And then we're going to summarize it all in this sum here. Does that make sense? Okay, speak now or go back in your notes later. Okay. Of course, it would be exact if this sum was equal to this expansion. Then it would be exact because then you've been doing full infinite Taylor. Obviously, you're not going to do infinite Taylor. Okay. First order Runge-Kutta looks like this. It's called the forward Euler method. Explicit Runge-Kutta. Forward Euler says, given that I have dy y by dy t is equal to something, right? Dy y by dy t is equal to y, right? Super easy. What I'm going to say is that y at I plus 1, the next time step, is y at I, the current one, plus whatever that function was, only the right-hand side, times my time step. So if my function was dy y by dy t is equal to, I do. If I have dy y by dy t is equal to, let's throw a constant out there, a times y, right? If a is negative, that's exponential decay. If a is positive, then it's exponential growth, right? No problem. What we're going to do, explicit Euler is going to say, forward Euler is going to say y at t is equal to 1 is equal to y at t equal to 0 plus dy y by dy t evaluated at the current one. So this would be dy y by dy t at t is equal to 0 which means okay. And using our more condensed notation, what that's going to be is y at I plus 1 is equal to y at I plus a y I. Oops, I need time step here, h. Okay, good, excellent. Explicit Euler, almost entirely useless. Okay, Wen's method, take a look through it. It's interesting because it iterates. It's what we call a predictor corrector method. We're going to get that more into in multi-step methods too. The idea is that you take a guess and try and use your guess to refine and basically throw the midpoint at it. You could also just throw the trapezoid rule only for a special case. Look at the notes. Midpoint method is the first one where instead of taking your full time step going from 0 to 1, you go from 0 to 0.5. Calculate the slope at 0.5, and then use that to take the full step from 0 to 1, right? Again, we're back to taking that full step. That's what makes it a single step thing. Take a look through that. Runge-Kutta, are there any fluid dynamicists in the room? Anybody who really gets into thermal hydraulics and really likes doing fluid flow and stuff like that? Fluid flow is all over explicit. Okay, so you guys make sure that you guys will almost definitely be seeing Runge-Kutta 4.5 like for a good long time at this point. I'll explain why that is on Friday. Okay, everybody else will be doing BDF. Okay, actually that's a bit too specific. Yeah. Anyway, okay, moving on. The whole idea of Runge-Kutta is that we have this. The midpoint rule was interesting. The midpoint method was interesting because we took a half step, calculated the information there, and then used that information to take the whole step. And in doing so, we achieved higher order answers. Order h cubed locally, integrating again, so you lose one order of h, and that you get order h squared globally. Runge-Kutta generalizes that. I'm not going to go through the math because this was Monday's lecture. Look at the video, look through your notes. You introduce something called this butcher tableau. I do need to go through this one. I need to go through quickly because it comes back with the implicit one. The butcher tableau is the formalization of this whole process. It's ugly. I'm going to say like these things are super, super ugly, but you chuck them into a machine and the machine knows what to do with it because it's algorithmically put there. So butcher tableaus are nice because they're like condensed. The explicit family, this is a lower triangular matrix. That's the magic that I need to get to. And what that means is that the next step is only determined by the previous steps. And the idea is that you take small steps forward based on your previous information, and you try and walk your way through the solution. So take a look at that, watch the video. I'm just going to quickly go through the Runge-Kutta 4 method in very, very, very light detail, right? This is the actual equations that you end up solving. They can be solved sequentially, right? Not as a system. That's the magic. Here's your butcher tableau. Okay, so this is the idea with RK4. If people talk about Runge-Kutta method, chances are they're going to be talking about RK4. Otherwise, adaptive Runge-Kutta, and that's RK4.5. I'll get to that one in a second. So the way it works is that I want to get from T0 to T0 plus some delta T. I have my current value. I'm going to find the right-hand side of my equation over here, and I'm going to take my first slope. I'm going to calculate my first slope. That's going to be K1. I'm going to take a step from my first point all the way over this slope over here. And then I'm going to repeat that. I'm going to turn the crank again. I'm going to find a new slope. That's going to be K2. I'm going back to the beginning, taking K2 all the way over here, right? Which is now going to be different following the K2 slope. And now I'm going to calculate K3. That's my third slope. Then I'm going to take K3 back from my beginning, right? Go all the way over here, calculate K4. That's my fourth slope. And then I'm going to shake them all together to get this final guess, which actually turns out to be a good guess. Easy. No. I find absolutely no value in asking you guys to memorize this sort of thing. Like this is what Wikipedia is for. This is what packages are for. Okay, so you look at that. The important thing to understand here is this idea that we're gaining accuracy by taking the substeps. You guys have all done my midterm now. You should be at least passingly familiar with what I'm hoping you get out of this course, right? Conceptualize that you're taking these little steps to get through there. Okay, so the RK methods, the explicit methods walk forward, right? Hence forward method, forward Euler. The magic is that all of these, you're using that information to estimate and cancel out your higher order derivatives. And that's good. And it works. RK4, by the way, is actually order 5 accurate, which is fantastic. Over this interval, you chain them together and you get order 4 because you've lost an order of h. Yeah. Yes. K3 is also wrong. So I can't say that it's a better prediction than K2. But the combination of K2 and K3. So think about it this way. K2, sorry, following K1 got us here. Following K2 got us here. Right? So somewhere in between, we've bracketed it. We've got a little bit too low and a little bit too high. Somewhere in between is the right answer. Right? Meanwhile, we can also calculate the slope over here, which is also wrong. Right? This also isn't the slope of this curve at this point. But we're doing that you know how I described before with the left Riemann sum and the right Riemann sum? Like one was too low, one was too high. The answer is somewhere in the middle. That's what we're doing again. But we're doing it in a much more sophisticated fashion. But by following that RK method, you're doing that kind of on like the proper mathematician way. Yeah. Yes. Yeah. Yeah. That's it's kind of weird, eh? Like this is RK4, and because you have these zeros along your, I mean, this is a diagonal thing, right? And there are computational implications why you do that one too, right? You're going back to the beginning and you're ignoring your previous one right until the end, which is a little bit strange. It's a little bit strange to do. RK45 is even worse. This is the simple one. Okay. So this is still a single step method because we only had this. And at the end of the day, we're only going to find this one. Everything is calculated from that part forward. We don't have any historical considerations in there. Okay. Some of you might be thinking, why bother taking there are a lot of function evaluations in this. Why bother taking a single step all the way h? Why not just take 2 half steps? Anybody thinking that? I'll assume everybody raised their hands on that one, right? The reason is that is effectively what RK4 is doing, but it's doing it internally. It's doing that hidden, and it's combining those results smarter than we would normally. It's not just about taking smaller steps. It's about using that information to cancel out our other errors. Okay? There is a hidden assumption in this, that being that this curve is nice and smooth, right? If you have a function that looks like that, right, this one is actually not so far off from that one. And it's actually not so far off from that one, right? If this is a single time step. If you add a curve that does one of these, right, this one is dramatically different from over here, is even worse, like, right, positive, 0, negative, terrible. So if you throw RK4 at something like this, you're gonna fall on your face. Okay, it's gonna throw this massive error because your hidden assumption isn't really true. And now you need to cut the step size. Now you need to bring it back, which gets us into adaptive time stepping. All right. So This is an example of a case where you would need adaptive time stepping. First of all, adaptive time stepping is great because sometimes functions do slow things, and then all of a sudden they do fast things, and then they do slow things again. And this is by sometimes, I mean almost always. Consider driving in a car. You're driving, stop. Driving, stop. Right? Can you imagine if your GPS or your self-driving car just kind of integrated over that stop? Right? Like it would be a big problem. Okay? So the idea is if you just did a vanilla stepping over here, you could just step over this shot entirely, this uptick, and then you would probably actually continue somewhere down here because this is time dependent stuff, right? Which is just completely wrong. Okay. Adaptive time steppers automatically adjust their step based on some kind of estimate of the error. Estimate of the error is a very loaded question. We spoke about how you estimate error before. There are kind of the more formal methods, right? Relative tolerance, absolute tolerance, that fun stuff. And then there are the more heuristic methods, I would say. But let's talk about them. Okay. So the idea is that you have a current time step. You have some estimate of your current error, and you know what your error should be. This is a tunable parameter. Right? You never say that it's as good as it could be because then you're just stuck in an infinite loop. You want to say, I don't know, 3% error is my error tolerance, right? Generally, you would want that lower. And then you raise it to this power. You raise this fraction to a power. 0.2 apparently is a good choice. Honestly, it's a bit of dealer's choice, and a lot of the more sophisticated methods will have like implicit methods to choose that sort of thing. But there are other questions. If you took a time step and it turned out that you were uncomfortably wrong, right? You estimated the error and it wasn't so great. Would you disregard that time step? Is it garbage? Or is it still useful? Right? Could you correct it? Could you take what your solution was, estimate the error, subtract it off it, and now you get a better answer, right? All of these are down to your different function algorithms and your choices. Right? It's easy enough to say when your function is y is equal, y by t is equal to y. Super easy to evaluate. Again, if you're doing some super sophisticated console model where everything takes like an hour to run, disregarding that solution might not be a good idea. Now you're putting it onto an HPC. It costs you a lot of money. It has 2 million cores chugging away for 2 weeks, and you get the wrong answer. What then? You know, you don't want to throw out that information. That's expensive information. Okay. How would you catch non-convergent cases? A lot of the times you guys found out in computational multiphysics, sometimes your solver just laughs and dies, right? Doesn't even converge. What do you do then? Yeah. One of the answers that you could do is just have one of the ways that you could formalize characterizing the error is by having the time steps, right? So you take yours, you either do a double step or you take a half step, and your error, you take 2 half steps compared to your full step. And because we know the order of error between the full step, right? If we were doing midpoint method, for example, right? That's order 3 locally, order 2 globally. So the first time step would be order 3. If we did 2 half steps, that would be order 2, right? Because we've gone the first one as a sum of those 2 ones. We compare that, we get an error. Okay, this 16 comes out because of the expansion and the fractions, right? And we could get some kind of estimate for what the error would be. And if we really wanted to, we could correct the first one. We could correct one of them for the better one if we wanted to. Okay, so this is an example just to show you guys what I mean. This is just an equation that I cooked up, right? y by dt, you can read that. You've got an exponential, you've got this guy over here. Okay. Our case step, this one is a manual implementation because I wanted to show you guys the rates, but there is RK4 in the, I think it's SciPy, might be NumPy. Okay. After the time stepping, if we do 1 time step with h is equal to 2, right? So our time step is 2 seconds, and we do that in a single shot. Our answer that we're going to get is 15.1 compared to 14.8 is the true answer, the analytic answer, right? And we get some value. Or we do 2 time steps, both with 1 second, and we get a slightly better answer. Okay? And then we can analyze what the error should be without information of the correct answer, without information about the analytic answer. Does that make sense? Okay. So when you do that, you had to evaluate your function. Remember, function valuations are expensive. You had to evaluate it 8 times. Why 8? Because RK4, every time you call it, calls the function 4 times. You've got it here, you've got it here, you've got it here, and you've got it here. That's 4 different function evaluations. If you do that twice for your double step method, then you've called it 8 times. That's expensive. Could you do it smarter? Yes. Runge-Kutta Feldberg came up with the idea that he's going to throw RK4 and at the same time calculate RK5. We didn't talk about 5. Technically, you could go on and on and on. There are reasons why you wouldn't. It's because the entire problem becomes ill-defined and you're basically just shooting in the dark for magic numbers, right? But luckily, there is a solution exists, right? This is the Butcher tableau. At the end, you actually end up calculating your function 5 times, but you combine your weightings intelligently, right? Notice that there's a 0 down here. There's a few zeros here. So what you do is you calculate it 5 times, and you consider that as an RK4 method, and then you use the same information to calculate the RK5. So you have your RK4, which is 5th order, and you have your RK5, which is 6th order. You calculate both those numbers at the same time. You get your error from that. Here's all the math in case you're interested. And then you can even correct it. You've got a high order approximation. You've only evaluated your function 5 times. You've got a high order approximation because you've corrected your better answer, right? But you've also got an estimate of the error, which means you can go back and change the time step. Actually, they don't bother going back at that point. They usually go forward, right? So you've got a very good estimate and you've got an estimate of your error, so you adjust your time step accordingly. All in 5 iterations, all in 5 function evaluations. This is the one that a lot of you guys are going to be using. RK45. Don't bother trying to memorize this. I mean, you can if you really want, right? But it's fugly. Okay. Let's see. Yeah. Okay. And yes, it works. There are other ways. There are other ways that you could check whether or not you want to have your time step. Whether or not you want to change your time step. Anybody think of any? I already hinted to one of them. Anybody, class, anybody ever watch Ferris Bueller's Days Off? Have you seen it? Yes, 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 yes. There's a scene where it's like the prof is in the class and he's teaching history and it's like, class, anyone, 1940, anyone, 42, anyone. It's just a super great movie. I don't know what happened to those actors now. Okay. What if your solution dies? Right? You're running COMSOL, you've run some big model, it goes, can't converge. You've got 9 steps, 9 time steps, you only wanted 10, and on the 9th one, it dies. Has that ever happened to anybody? Right? What do? What should you do? Okay, I'm going to throw one more piece of information into this mix. All of these things, even with the explicit time steppers, what you're doing is you're trying to you end up trying to solve. Well, actually, no. Explicit time steppers, this isn't so important. It's more the implicit cases because then you're actually solving the system. Okay, I'm just going to give you the answer here. You could throw iterative solvers at it. Okay. Given a solution, typically speaking, your next solution, your future time, is going to be somewhat related to your current solution. You wouldn't expect to find your car here, here, here on the other side of the earth, right? It just like when that, like when you're driving on GPS in the city and all of a sudden you're like 3 blocks away and then you scoot back and, right? Like that doesn't happen in reality. We talked about iterative solution methods, and we talked about the better your initial guess, the faster you're going to converge to your solution, and sometimes even the more robust. The same thing is true here, right? Given your time step, the smaller your time step, your initial guess for the next solution is just going to be your original time step. So when you make it smaller, yes, you are changing with the accuracy, but you're also going to make the next time step easier to solve, which is also nice. So if you ask for too much of a change, your solver might just die. Explicit methods, that's not so important because it doesn't involve solving linear systems. There's no root finder with explicit methods. So generally speaking, that's why you want it for fluid flow, because Navier-Stokes is a nightmare. With implicit methods, spoiler, we're going to get into root finding, obviously. One of the ideas that you could do, and one that I use all the time, you have an exception catcher. If model dies, cut time step, rerun. Easy as that. All of a sudden you have a failsafe. So that is a great one. And if you ever get into that one, absolutely have like Python try catch. Super, super easy. All you do is you just catch that exception, say, nope, didn't work, go back, try that again. Another way you could do it, which is honestly pretty crude, is if you're throwing some kind of iterative solver at it, monitor your iteration capabilities. How many iterations does it take, right? With Newton's root finding method, the closer you are to your solution, the less iterations it's going to take. Same thing with your iterative linear solvers. The closer you are to your solution, the less iterations it's going to take. So you watch that and say, as long as my iterations are only on the order of 10, then I'm still okay. If it takes 2,000 iterations to find that root, I'm probably taking too ambitious a step, right? This is not a formal method. This is very much an engineering approach because math, right? Engineering. But personally, I find these ones really, really useful. Everybody on board? Now we can actually start with today's lesson. Okay. We have been talking about explicit methods. We're using the current time step and the information at the current time step to predict the next. There is an alternative. That is implicit methods. And it actually turns out that this is pretty much a lot more correct answer to use. Okay, what we're going to do is we're actually going to use, so here we used the current time step to predict the next, we used our current solution and the slope at the beginning to predict the next one. Now what we're going to do is we're going to use the slope at the end and the solution at the end and make sure it lines up with the beginning. We're looking backwards and we're solving it as an implicit equation. That's where the term comes from. And the backward Euler method is honestly like that. That's a very, very useful tool of choice. Okay. Unfortunately, when we're solving implicit systems, right? How do we solve implicit systems? I'm sure you guys are like still doing this a little bit from midterm paralysis, right? How do you solve an implicit system? It becomes messy. It becomes nonlinear. How do you solve nonlinear systems? Begins with R, ends with oot. It's not root, right? Root finding. All we're going to do is we're going to cast these things as nonlinear equations, ultimately nonlinear systems of equations, and then we're going to throw our root finders at it. Does everyone remember how to do root finding? You should. That's why this is the second half of the course. Okay? Backward Euler method looks like this. The next solution, y at I plus 1, is equal to the current solution plus whatever the slope is at the next solution, which is a bit funny to think about it, right? With this one, it's the reason why I wrote this down, right? You have dy by dt is equal to ay. This is forward Euler because we're going to say y is equal to yi plus 1 is yi plus h a yi. What backward Euler is going to do, yi plus h a y I plus 1. This is forward. This is the backward one. Okay? So when you're going forward, all you ever need to calculate for your next one is just yi. When you're going backwards, your solution is implicitly defined. Backward Euler is actually super trivial with this. In general, it's not. It's not at all. Right? We're going to rearrange that and use that to understand something kind of nifty. Okay. Numerical stability. This is an important thing for you guys to understand, so I'll probably end up reviewing this on Friday too, just to make sure. An algorithm is numerically an algorithm for time stepping is numerically unstable when small errors. Actually, that's more general, isn't it? An algorithm is numerically unstable. Any kind of iterative algorithm is unstable if errors accumulate and grow and magnify time over time. They can occur because of things like discretization, right? Your time step, round off, truncation error. We've been through all these sources of errors. So this is not working. So I'm going to kick it over to Colab. And I'm going to tell it to run all. Yes, run all. All right. What we're doing here, we're solving the simplest differential equation ever. Okay? What is the solution to this equation? Right? Exponential decay, super well behaved. It doesn't get any simpler than this. Okay? If you throw an explicit time stepper at it, so we're going to throw explicit time stepper and an implicit time stepper at this thing, okay? 4 different step sizes. The analytic solution is in the dashed black line here. It's not going to change. It doesn't change depending on your time step because the analytic solution doesn't have a time step in it. It just has a time, right? No problem with that. This problem doesn't exist in analytics. It's strictly a numerical issue. As we increase the time, as we increase the time step, the explicit Euler is down here. It becomes like a kind of a worse solution, but not terrible. At least it captures the general idea, right? The implicit method is a bit better. Okay, we're going to get better and better and better. And all of a sudden, our step size gets too big. But at least it recovers. It steps too far. The slope here is too great. It overshoots, but then it kind of self-corrects. And it comes back like this, right? Meanwhile, the implicit don't care. Implicit is just stepping along. Increase that time step a little bit more, right? We're getting more and more and more overshoot. This is starting to get bad, right? This still isn't bad because at least, yes, we're overshooting, but at least it's correcting itself. At least it's coming back to the real solution, which of course is 0 for exponential decay. Check this out. Time step 2, it no longer corrects. Past 2, that error blows up. This is the bad one, right? Because all of a sudden, like explicit Euler just fails, and it fails catastrophically. You cannot trust this thing. Meanwhile, implicit Euler is actually okay. What's that? Gadzooks. Notice. For small time steps, this was actually okay. Explicit Euler is a perfectly fine answer. RK45, explicit RK45 is perfectly fine for small enough time steps. It is when the time step gets too large that we start to have a problem. Okay? That's why in a lot of applications, we'll come back to this more later, if you want to use explicit is much faster to solve because you're not doing a root finder. You don't have to worry about convergence. You don't have to worry about any of that, but you're kind of handcuffed to these small time steps, as opposed to implicit solves that can take much larger time steps. Okay. Let's actually run these numbers. Let's actually see these equations. I'm hoping to get through implicit Runge-Kutta today still. Okay. Let's just throw this in this calculation here. Okay, what we're going to do is we're just going to follow this equation for the forward Euler scheme, right? Plug in our values, and what we're going to get is yi plus 1 is equal to yi times this factor, 1 minus ah. Okay? In order for the solution to follow strictly decreasing behavior, right? Exponential decay, we have this limit left on, we have this limit set on our time step. As long as h is less than 1 over h, then this term is small, is some fraction. This is not the correct formal one. We'll get to the formal one. This is the easy one. Okay? As long as this is small, then this bracket is smallish, right? And this thing will actually decrease nicely. Okay? If h is between these two bounds, it will overshoot, but then it'll correct itself. That sign will flip, you'll end up canceling that out, and it'll get back to 0. No problem. If h is greater than 2 over a, in the previous example, that was 1, h went past 2, and all of a sudden it catastrophically failed. Then we have a problem. With the implicit case, now we have yi plus 1 over here, and just by doing that implicit switch, we make this 1 over. And 1 over is essentially always going to be some fraction. Doesn't matter how big it is. All of these are positive numbers, therefore that will always be positive, and that propagation from one time step to the next will always be some kind of fraction. It will never have a problem. It is called unconditionally stable. Right? So the numerical stability is placing, notice the warning alert, right? Listen to this one. The numerical stability is placing a limit on the time step that you can use. If you have a lot of information about your problem, then that time step is well characterized and you can control it well. Hence, it's actually used in a lot of cases because it is actually very fast to calculate. Okay. And the idea is that because with the implicit methods, since you're looking backwards, it's easier to find, no, it's more robust to say that that solution is actually real. Because whatever that solution is, if you look back, created that one, it becomes a lot more easy. This broaches into the idea of numerical stiffness. Both hands, both alert warnings are flashing on this one. The stiffness of your equations is related to, is a big problem that you're going to have to come to terms with when you're doing these sorts of numerical methods. It's algorithm. It's not your equation. The math don't care, right? Stiffness does not agree in mathematics, in reality. Stiffness is an algorithmic property, okay? But we need to avoid it, right? The way that I like to think about it is in terms of different time scales, because that's my mindset. So what's happening with stiffness is that when something is happening faster than something else, you have some kind of transient, right? You're driving, you stop. You drive, you stop. Your reactor is operating normally. You have a fast transient, then you're back to normal operation. That fast transient, that sharp behavior, is what kind of the one of the warning alerts that you're going to have a stiff problem. It's not the only one. Sometimes stiffness is just there regardless, but this is at least one of the criteria that leads to it. Okay, and the problem is that this happened with exponential decay, exponential growth. It doesn't get any easier than that. And even worse, is this just this one? Yeah, okay. Back to the collab. You might be tempted to think, so here's an equation, here's our differential equation, here's our analytic solution. I'm not going to get to implicit Runge-Kutta. Have to pick that up tomorrow. You might think, so this is an example of something with a fast transient. You have right from the beginning, you start over here, you go whoop, and then this kind of nice slow behavior. So what you're going to see is that one of these terms, right, is going to be the fast one, right? Exponential growth. And then your kind of slow, tottering like behavior kind of kicks off after that. This slider, I think, is just the size, right? Yeah, so this slow behavior like continues on and on and on. But as you get down here, you can see that this it isn't just a blip. This is actual, like this is an actual thing that you have to calculate. But at t is 0.01, at least it's over. So how about you just skip it? Let's just skip it. Let's just pretend this didn't happen. Let's just start off our iterations at t is 0.1. That sound like a good idea? Obviously, it's not. Stability of the term with the forward Euler requires that this time step, this is the same analysis. I'm already over time. Just kind of skip it. The problem is that even after that's done, even if we start at 0.01, we're into like the nice part now, right? The fact that this term still is in the equation means that as we get to larger and larger time steps, that term is going to reactivate. Even though it's out of the picture with the solution, it still exists. It's still in the equation. And if you try and switch gears and jump over to an explicit, it's going to say, hey, yo, I'm still here. And it's still going to take your answer. Which means that you got to be careful. Super quick, while you're packing up, stiffness is remarkably poorly defined, right? It's one where it's related to this numerical stability. It's really problematic and really kind of rears its ugly head when you have these short transients. One of the ways you could avoid this is just ignoring that term. If you know that you're past the initial value, that initial transient, cut it off. You're done. With acoustics, you do it all the time. Technically, elasticity is actually a wave equation, right? Sound waves. That's how sound works. But we just ignore that part. We just cut it off. We just make it quasi-static. You could do that for steady state with diffusive equations too. Or you could throw implicit methods, which are more stable, but they cost a bit more. We'll pick it up from here tomorrow. Okay. Let's see. We are broadcasting. I am sharing. This thing's on. Okay. Let's go for, let's finish up the initial value problems. I have assignment 4. It should be released on A2L. You've got until next Thursday, end of day, Friday at 8:30 to do it. I'll quickly walk through that one. And midterm marks are going to be released any day now. I need to I need to get on that one and just check off a few things. Okay, so last time we talked about backward Euler method. Remember the idea was instead of if we're at this time here, normally you would say the explicit answer to do that is to take that time and look forward and predict that. But that has all these errors with error accumulation and gets catastrophic when your time step is too large. Time step is small, that's okay. We're actually going to derive that condition, what that condition is, in later units. I think when we talk about partial differential equations, we'll get to that one. So that'll be next week, actually. But generally speaking, that time step is going to be super, super small compared to your implicit methods, when what you do is you start off at this time and you say, what is the answer over here? Consistent with that one, right? So it's a little bit of a twisted way to look at it, but at least the naming is good. It's the backward Euler method because you're looking backwards. But now you have a situation where you're trying to solve for an answer while using that answer, which means it's implicit method, which means you're into a root finder. Good thing for us, we have root finders already. Okay. So the idea there is, yeah, so we start off at yi, we're looking for yi plus 1, and we're using the information at yi plus 1 in order to find a consistent solution. Deals a lot with stiffness. Stiffness itself is very hard to define. It's one of these concepts like there isn't really, it's like the pathological functions. There's a lot of competing answers to it, of what this thing is. Generally speaking, it's why a difficult problem is difficult to solve, which is super not helpful. The one that I encounter personally is when you have different phenomena happening on different time scales, because what you end up happening is something that is happening quickly, and all of a sudden all of a sudden it kicks up a fuss. So I'm trying to think of a good example with that one. I can't think of a good one this morning. Sorry. And the funny business is, and that was this example here, even after that, so usually what you're going to get is some kind of solution with like a fast part and a slow part. That's very, very typical in physics. And you would think that after that fast part is over, then you don't have this problem anymore, but guess what you do, right? So that's going to place a lot of limitations on the sorts of calculations that you can do robustly and the numerical answer to do this. This is a property of the algorithm. It's not a property of the equation, right? That's why you can throw implicit methods at this, which are much more robust to this, right? You can throw an implicit method at this and basically you don't have to worry about stiffness anymore. You can take much larger time steps and it doesn't just catastrophically shake itself apart. Okay, let's generalize our implicit methods. This is going to get super mathy, super fast, and then I'm going to invalidate it entirely, and we're going to do multi-step methods. So I'm gonna scream through this one. So previously we were talking about the generalized form of Runge-Kutta, right? The idea was that this is basically a Taylor expansion, right? Your next time step is your current time step plus some kind of Taylor expansion, and we're approximating that Taylor expansion with this H sum blah 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 curve, right? With the implicit methods, if you remember this, the Butcher tableau here, if explicit, it was just the lower triangular part, which meant that every future time was calculated only based on the previous times. Implicit Runge-Kutta is the same idea, but now we're solving for the future times all at once, which it gets super complicated because not only are you solving one implicit equation, but you're actually solving for multi-steps in between, the subdivision of steps in between those ones too, simultaneously. So you're not just solving for one, like for the equation, the solution at time t plus 1. You also end up solving for the solution at time t plus 1/2, t plus 1/4, t plus 3/4, and you have to solve that monster system. It becomes super impractical, to be entirely frank, and not worth it when you have multi-step methods. So the derivations are here. The implicit Euler method, this one is actually what I use in general. To be honest, implicit Euler, that's the backward Euler. That it's basically foolproof. You just throw it at it. Chances are it's going to be unconditionally stable, and you're just going to gain benefits, and you're just going to be done. And you can always cut your time step. And if that time step is small, then you just restart your calculation, and chances are that one's going to converge anyway. Yeah. There are other ones. There are the implicit midpoint methods. Bowen, I was expecting you through the door. What happened? Right? There are the implicit midpoint methods. You can look through the derivation if you like. These are the Butcher tableaus. Implicit trapezoid. This is the Crank-Nicolson method. If you guys have come across Crank-Nicolson, we're going to come back to it when we talk about partial differential equations. It's kind of one of those quintessential ones. This is actually a mixed method because you end up taking a blend of your past time step and your future time step and solve for it together. We'll come back to this one. There are two-stage ones, the Gauss-Legendre order. This is it ends up using the Gauss points for integration as part of this thing. That's why you have all these funny square roots and weirdo values here, right? You see that the form is pretty complicated. I think I even just linked to the Wikipedia method here. Take a look at that if you're really keen on it, but honestly, my advice is just to skip over to multi-step. Okay. So up until now with the Runge-Kutta and the generalized explicit and implicit, all those are single step methods, right? We're here, we're stepping into the future, and we're ignoring our entire history. Okay. Multi-step methods are the opposite. We actually use that history in order to try and get a better solution. Okay. So the way it works, right? We're doing the same time integration, and we have formulae for that integration. We covered numerical integration. Let's use some of those, okay, with our history. Now there's a little bit of a problem with history, okay? Because when you're starting off your calculation, you don't have a history, right? You only have your initial condition. So you need to bootstrap things, is the term. There are a few different ways to do it. There are explicit first steps and then bootstrapped into implicit methods, so on and so forth. But I'm going to come to the one that it's called BDF, that like COMSOL is using, by the way. So you guys have already been using the implicit multi-step methods. That's BDF. That's what COMSOL uses. We'll come to that one and why that one is the method of choice. Okay. In general, this is kind of a funny form, but this is just like they had the generalized Runge-Kutta form. There is the generalized multi-step form. It looks like this. Okay, so what you have is some kind of weighted sum of your previous time steps and your current time step. Sorry, and your future time step. So what this is you're taking your previous solution. So you're at time time 10. So you're going to go back a few time steps, 7, 8, 9. You've got your current one, and you've also got your future one, which is what you're actually trying to step into. That's all baked into this term. And then you have your solution of the differential equation that's also being weighted by this set of constants. I'm going to break this down so that it actually becomes clear, but this is the generalized form. And these are kind of like matching up with the same steps. Okay. A, J, so these sets of constants are chosen for accuracy and the balance of computation. Because with implicit Runge-Kutta, you had this basically multiplying by a factor of 4. Whatever your solution expense was, you had to do that 4 times for a single time step, which is why it wasn't worth it. Okay. Let's see. So what we're interested in is yeah, okay, so that's a normalization of these vectors. I wouldn't worry so much about that. When BS is 0, so this is the current stage, then the final solution, which is the one that we're actually looking for, is only dependent on previous solutions, right? So what we're going to have is we're going to have yi plus s, which is the step that we're looking towards, and that's only going to be a function of the solutions from the previous steps. So it's an explicit method. Problem with explicit is stiffness, right? Stiffness is always going to sink explicit. These ones are no exception to it. Okay. Sometimes the scheme is used to generate a predictor. We ran into the predictor corrector cycle with Wen's method, which is also an explicit method. So the idea there is that you take an explicit step, which is generally cheap to do because you're not solving for anything implicit. There's no root finder, there's no optimization, anything like that. You're extrapolating out a solution, and then you're correcting it according to some backward-looking calculation. Okay. Yeah, it can be corrected basically through that. It doesn't handle unevenly spaced steps. Since you have H out here, right? H is going to be your time step associated with the time integration, right? There is only one H though. So if you have different time steps, this isn't going to work. This only works if you have a single H, a single time step frequency, which in general you're not going to have because that flies in the face of adaptive time stepping. Okay. It also doesn't self-start because there isn't an easy way that you can just include the previous information into the current one. And anyway, explicit single step methods generally outperform them. So these guys are generally not used. Don't use these guys. The ones that you do want to use are the implicit linear multi-step methods. Blah. What you do is you say that all of these beta constants, I hate when you're doing like, have you guys like started to read like academic papers and stuff like that, like research papers, right? You know how like they build out like this general mathematical framework and then they just make a whole host of approximations to make it like actually digestible. Have you seen that? Right? Like I run into this stuff all the time and I'm sorry to have just done this again here. Okay. What we're going to do is we're going to set every single beta equal to 0, except for the next step. So all of these terms disappear, except for the current one. Okay, I'm going to show you what that looks like. It is better known as the backward difference formulae, BDF. This is the one that COMSOL uses. It's the default for a lot of these things, the general ones, not the fluid dynamic ones. Come back to that one in the summary. Okay. Starting from this idea that just dy by dx, I need to change x to t here, right? That y by t is equal to f of ty, right? The alpha coefficients are the derivatives of the Lagrange interpolation polynomial. You know how I kept saying that interpolation polynomial just keeps like coming back and back and back? This is another case of it. So what you're doing is you have your previous time steps. You are fitting, say you have 4 previous time steps. What you're going to do is you're going to fit a 5th degree polynomial to it. Sorry, 4th degree polynomial. If you have 4 of these things in your history, you just fit a polynomial to it and use that to extrapolate your next time step. Makes sense, no? You bake in a little bit of information of that system at that point, and that's what makes it an implicit method, right? So this is quite literally, it's kind of obvious when you think about it. If you have a solution that looks like here's 1, here's 2, here's 3, here's 4, and you're wondering where this guy is it going to be down here? No, right? Is it going to be up here? Probably not. Where is it going to be? Right? Like this is kindergarten. We're literally playing connect the dots here, right? Except now we're encouraged to color outside of the line. Okay. We can find, for example, right? Again, this is one of those things like I'm never going to ask you to like know these coefficients. There's no value to this sort of thing. These are the first 5 orders. So if you're only looking back once in history, you're going to say that the current one is equal, or sorry, the next time step is equal to the current plus your step and then your solution at that other one, at the next time step. Okay? Does this look familiar to anybody? BDF order 1. Okay? This is what we started with. This is backward Euler. Okay? Backward Euler backward Euler doubles up. It is the first order implicit Runge-Kutta, but it's also the first order BDF. That's what makes it so fundamental. When we do the second one, right, we're expanding out those coefficients. Now we're using the current time step in the previous one, but we're only using the solution at our next time step. 3, 4, 5, all the way over here, you get a lot of these nice funny coefficients out here, right? We've got the current time step, previous, 2, 3, 4, but we're still only using the solution at the next time step to solve for that guy. What this means, H only appears once because we've set all the other betas to 0. So this guy is completely flexible. There's absolutely nothing here for the time stepping. We can use whatever time step we want, which is fantastic, and it don't even enter into this. It doesn't enter it at all. We can use this no matter what. It is implicit and therefore good for, right? Good for stiffness. We don't have to worry about that. And you can even dynamically change between the orders. You don't have to choose an order and then just go with that for the rest of your life. If one is going to have a better result than the other one, then you just switch it. What you do is you take an error estimate and you do a little calculation off the side. This is what COMSOL does, right? Did you ever see the log in COMSOL, right? Like when you're solving a long problem, there's like a whole text file that starts to spit out. One of those fields is the current BDF order. And what it's going to do is it's going to, first of all, when you start, it's going to start off at 1 because you only have the initial time step. Therefore, it has to be BDF 1. This is a self-starting algorithm. You don't need to bootstrap it. Okay. And then what it does, as it builds up a history, it's going to estimate what the solution error would be if it took BDF 5, 4, 3, 2, or 1. And based on that estimate, it's actually going to solve for that. Isn't that cool? right? You can estimate the error before even solving for that solution itself. And that way it can take opportunity of this of these heuristics and get a good result out of that. Any questions? PDF. Okay. I'm gonna come to a summary of the initial value problems in a minute here, and then we'll talk about the assignment. Oh, I hope this updated. Did that update? Yeah. Okay. Reduction of order. We've only been talking about first order ordinary differential equation y by dt. Right? In general, you're going to have more than that, especially for wave equations. You're going to have, right, your second time derivative, an acceleration. This is a wave equation. The way you do this, I think I remember asking you guys, and you had already done this before, is you split up that order. So what you have to do is you define a new variable, right? So if we have y double primed is equal to something, right? That something depends on y and y primed. So standard wave equation. What you're going to do is you're going to define a new variable. Where's my system of equations? Doing this in the wrong order. Hold on a second. Okay, give me a second. Back up a minute. Adaptive, no. System of equations. I don't know why that's not showing up. Okay, there's a bug in building the book, but I'll come back to that one. I'll correct it when I get back to my desk. Okay, before we go there, systems of equations. Put a pin in the reduction of order part. We've only been talking about one variable, one unknown, y, right? We could, in general, we're going to do multiphysics. We're going to do reduction of order, right? We're going to have different unknown variables that we're going to be solving for, right? y1, y2, y3. The good news is that all this stuff generalizes exactly. All you do is you make your variable a vector. Now you're solving for a vector of unknowns, and it just goes through trivially. There's actually very, very little modification you have. There's no modification to the conceptualization. And if you implement your method right, I wouldn't bother implementing anything with the exception maybe of backward Euler, which is easy to do anyway. All you do is you just replace these things by vectors, right? So what you're going to have is you're going to have a whole series. Notice that you can have on your right-hand side mixed derivatives. You can have temperature depending on concentration depending on temperature. Boom, 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 boom. And nothing really changes. You just slap your vector notation onto your solution. Everything works exactly the same way, including BDF. Right? No problem whatsoever. That's the good news. Okay, now we go back to reduction of order. So with reduction of order, when you do have a second time derivative, the name of the game is to define a new variable that's equal to one of your derivatives, right? So you're going to define z equal to y by dt. You guys did this before, right? Solving wave equations in differential equations, right? Exactly the same idea. You set new variable z is equal to dy by dt, and then you solve for those two simultaneously. Becomes easy. An example here is swinging pendulum. By the way, learn this, look at this. You're going to need it in about 10 minutes, maybe 15. This is the wave equation, which didn't format again correctly. The idea is that you're going to define your unknown vector to be your angle, right? I skipped a step here. So I'm just defining my unknown vector as being my angle and the rate of change of my angular velocity, right? dy by dt becomes this guy. This is the first derivative of the position. This is a function of the position over here. And then you solve for it, right? Pay attention to this one using RK45. The function here is in SciPy. It's solve IVP initial value problem, right? You give it your function, which is now a vector function. Everything generalizes. You give it your time span. You give it the variables that you're looking to solve, or these are the initial conditions, and you tell it the method RK45. Off it goes, and it plots you out your solution. Well, it gives you your vector, and then you have to plot out your solution. Questions about reduction of order? Okay, good. You'll regret that. Okay. Reduction of order is one of those things that it's like it looks confusing, and then you do it, and it's much easier than you expected it to be, and you're not sure if you did it right, but you actually did. It's just one of those things. Okay, let's do a summary because that was a whole lot of different options. Explicit methods, easy to calculate. They parallelize well. Because you're only using information that you have, you can split it up. You guys work on one part, you guys work on the other part, you guys work on the other part, and we'll get together at the end and stitch that all together. That works with explicit methods. But it suffers from numerical stiffness and instabilities, and that requires necessarily small time steps. Small is a vague word. We can actually give numbers to that. It turns out to be related to your okay, a little bit of an advanced peek. When we talk about partial differential equations, what we're going to do is we're going to talk about our spatial sampling, which is your mesh, and your time sampling, which is your adaptive time stepping, right? It turns out that the maximum time step you can take is related to your spatial sampling. There's a whole theory. We're going to go through it on the surface level anyway. You're going to get an answer which is going to show you that that time step has to be shockingly small. However, at least it parallelizes very well. So if you have things that you're interested in small time steps, for example, all of fluid dynamics, as soon as you're out of like kind of nice steady state laminar flow, you have things like vortices peeling off. You have turbulence. You have all this nasty stuff that causes a lot of grief when you actually try and like solve it, right? Whenever you guys were trying in ComSol with fluid dynamics, we had to use it a bit too much that I was comfortable with, but like you see, it's kind of nasty to solve, right? The modern approach to that with these tools is to use an explicit time stepper and just do very small time steps, because you're probably interested in all that turbulence anyway. You shouldn't be stepping over that, first of all, but also you parallelize like hell. So you just throw it onto a giant machine and you get basically linear scaling, it's called. So if you have 10 cores, you get a speed up of roughly, never 10, there's always some overhead price, right? But you get a speed up of 9. Or something like that, right? If you have 100 cores, then you get a speed up of a factor of like 90, something like that, which is actually pretty good, I've got to say, as opposed to implicit. If you throw implicit, depending on the way that you're solving that linear system, if you just solve it with LU, it's terrible. A 10 core, if you take a machine, you solve it with an implicit method, and you throw a single core at it, maybe it's going to take 10 seconds. If you throw 10 cores at it, 8 cores, right? Octa, whatever machine. It's actually going to take 15 seconds. It's going to take longer, right? Because the added expense of the overhead trying to coordinate all these cores is going to tank your performance increase. It's not until you get up to like 100 cores that you actually see some kind of benefit. And even then, it's only going to be a benefit. If you throw 100 cores at this, you might see a speed up of a factor of 10. Right? And that payoff is terrible. And as you keep increasing the number of cores, you're going to get less and less payoff. It's not even scaling linearly. Okay? But if you're doing things like multiphysics, right? You want that time step. This time step, the ratio of time steps between your explicit and implicit is honestly like a factor of 1,000 to 1,000,000. That's what it comes out with on the other side. So yes, every time step with an explicit method is super easy to calculate, but you've got to take 1,000,000 of those things, as opposed to a single BDF implicit, right? That solves for it directly at whatever time step you want. Okay, so this is just a game that you're going to have to play, right? Fortunately, unless you're doing this like by hand yourself, you're going to have some kind of software package that's going to have some kind of recommendations. ColumnSol has it built in. I think star CCM is a big fluid dynamics code that I think Novog likes, right? So like that one is, it's all about the explicit methods, and it's super optimized for that. It has preconditioners through the wazoo and everything else. Okay, implicit methods. I already spoiled this a little bit. Computationally expensive, right? It requires a root finder. Don't forget, this is also a hint for the assignment 4 too. Like, don't forget about everything you've done just because we've moved on to it. This stuff does build onto it. The fact that we have an implicit system isn't really a problem for us because we have the toolboxes now to solve implicit systems. We can already do this. They parallelize terribly, but they are much more robust to numerical stability. Again, with multiphysics, this is why ComSol uses this, right? With multiphysics, you have different physics. And different physics operates on different length scales, right? Elasticity operates at the speed of sound. It's much faster than diffusion, much faster than heat transport, anything like that, right? Elasticity is a bad example because you can make that quasi-static anyway. But like this is, even then, even with that quasi-static approximation still isn't enough to get around this stiffness problem. Okay, and this significant, I should have quantified this. This significant is like a factor of a million. Okay. Systems of equations are super easy. Hallelujah. Reduction of order is the usual weapon of choice for higher order derivatives, at least the way that we are solving them. Right? If we the industrial toolkits for like doing wave equations for, well, guess what the approach to doing like normal wave equations is in something like ComSol. Do you guys remember? Do you guys remember how we did acoustics? How we did optics? In ComSol, how we did quantum? ComSol? Yeah, it's generally we're looking at the eigenvalues, but even before then, you do the harmonic expansion. You say that the entire thing is harmonic. You say that your solution, if you guys remember this one, this isn't part of this course. So this is just a throwback to the previous one, right? If you have something that is y double primed equals blah, 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 you know you're into a wave. What you do is you say y is actually equal to some other function, y naught, which is spatial, times e to the negative I frequency time. This guy nicely ends up canceling out, and you have to do this for a few different frequencies, and then you have your entire solution. This is the harmonic expansion, and it's super convenient because then you just cross that out, right? And all you do is you find a few frequencies that you're interested in and solve it as a system of differential equations, right? So as soon as you go into waves, you have other tools in your box too. Let's see. Adaptive time stepping. You want adaptive time stepping. The same thing when you're mixing different scales, time scales of phenomenon. If you have something, we had an example that the solution looked something like this, right? Over here, if you want to sample this, you want to have like super fine time resolution, but over here, nothing's happening, right? So you don't want to be doing this. It's boring. Just step to the end. Right? That's adaptive time stepping. You can make it algorithmic based on the error estimates. Failing that, you can do something brute force and just say, take the largest, double the time step on every, this is actually what I do in my codes. I double the time step at every time. And if it crashes, then I go back and I have it. If it takes too long, if it needs too many Newton iterations, then I go back and I adjust the time step. Right? And that's like the engineering, like just hit it with a hammer. Hit it with a hammer until it behaves. Okay. You want adaptive time stepping, which means that you need a solution method that is amenable to adaptive time stepping. Explicit or implicit Runge-Kutta is not, right? Explicit multi-steps is not. So we're not so interested in that one. Okay, explicit Runge-Kutta achieves high accurate estimates if numerical instability isn't a factor. Not physical instability, right? Fluid flow is physically unstable because you have all these turbulence, vortices, all that fun stuff, right? This is the numerical side for that. Implicit RK has to solve a whole collection of these multi-step, the solution at the subdivided time steps. It's a nightmare. I have not seen a good, robust application that uses that. I have yet to see one. Not to say that it doesn't exist. Okay, but it has. That's incorrectly spelled. Exponentially increases the computational cost. Similarly, explicit linear multi-step methods have conditions that make them impractical. We don't really bother with those ones, but the implicit version, the BDFs, have excellent properties while exploiting the solution history, right? Because we have that information, we may as well use it. Plus, it behaves in a certain way you would expect it to behave in a certain way. Okay, my suggestions: know your physics. Okay. In general, if you're doing something like fluid flow, they're also so the other thing I do is microstructure predictions, something called phase field model. There are entire packages of codes that only use explicit methods for phase field models, right? Because you're interested in that parallelization, they put these on the German supercomputers and they're running these on a few million cores. That's great if you have a few million cores lying around. My machine has 4, right? If you don't know your physics, if you're doing something generic like multiphysics, right, you're not so sure about that, an adaptive BDF is the default, is your go-to, right? It bootstraps by itself, COMSOL uses it, it's super easy to program, and you're exploiting your tools. If you know that the system is non-stiff, right, RK45 is your tool of choice. It will give you much, much better performance than BDF. BDF is still implicit, RK45 is explicit. It will be much, much better if it works. It'll either work much faster or it'll crash super fast, and then you know that you should have been using implicit. If your physics has abrupt changes, right, backward Euler is what you're going to default to. That's what your BDF is going to, if your BDF is smart enough to check not just the error estimate, but the actual error between that, it's going to be cut back to, do you guys know what I mean by that one? I'm just going to, okay, I'm going to talk about that one super quick. Say you have, because COMSOL does do this, but I just want to raise this too. Okay. Solution 1, we want to know what the time over here is, right? We are confident, right? Because previously everything has been behaving nicely. So we're fairly certain that we're going to be able to do this. This is going to be roughly where we are. We know that if we do, right, you can calculate the error associated with these BDF orders, right? We know that BDF5 will give us a pretty tight one. BDF4 will be a bit loose, right? So we're going to go with BDF5. We calculate this value, but it's not here. It's down here, right? Oh, shit. Something happened. Shouldn't say that while I'm recording, right? Something happened. Something went like this. Mostly, at least I'm not dropping F-bombs, right? This is way outside the error predictions here, right? Something else has happened. Most codes, COMSOL included, will say, well, oh, wait a second. I found this solution. This solution is dramatically outside this one. I don't trust this time step. Kill it. Delete, go back, do a smaller time step, right? The same heuristic is going to say do this, and maybe it won't. Maybe it still won't follow that, right? Something abruptly is changing in the physics. They're all over the place. This thing is constantly happening in nonlinear systems. You cross some threshold, everything changes all of a sudden. Diffusion, right? Vanilla diffusion. As soon as you put temperature in there, your diffusion coefficient is Arrhenius, right? It depends exponentially on temperature. You have a 10-degree temperature rise, and all of a sudden your diffusivity like skyrockets, right? Like you have all this stuff, all these exponentials all over the place. Very common. Okay. What COMSOL does is it builds up inertia. So what it says is if this condition fails, it's going to limit the backward BDF order. So I'm no longer going to trust that this polynomial is nice and smooth and almost definitely going to be around here. Instead, I'm only going to assume something that looks like that. Or if it's really bad, I'm only going to assume something that looks like that. And if it's really, really terrible, if this changed dramatically from this one, I'm not going to do anything. I'm going to resort to BDF order 1, which is... Somebody give me the answer. I got 9 minutes to wait around until somebody says the words. What's my favorite one? Backward Euler? Backward Euler, right? Backward Euler is the foolproof one. Backward Euler is, it's all kinds of stability conditions, right? You go through these orders, there are like 6 or 7, or I don't know if there's that many, 4 or 5 at least, like numerical stability quantifications, and all of them are super, super mathy, right? Like backward difference, backward Euler is kind of the go-to. It's basically bulletproof, okay? Which means that honestly, it's a good go-to. If you're ever in a situation where you need to make your own solver, just do backward Euler. To go to, super easy to implement. If something does go wrong with it, if you don't get a very good solution, you kill it and you restart it with a smaller time step. No problem. Any questions? Okay. Next week, we are getting into boundary value problems.